the last topic in planning, partial order planning. Well, okay, next to last. We're going to talk about beyond strips just for a few minutes, but the last major planning algorithm to talk about. All right? This is trivial. Well, okay, it's not trivial, but I've already showed it to you, basically. It's to take the top of this picture seriously. Okay. So what was I doing in this picture? I had the goal state and the initial state, and it looks almost like an electrical circuit diagram, really, with little wires running in between little gizmos, and a precondition needed something to feed into it. And so here we had an action, do P, that achieved P. And in fact, we could even, if we wanted to, we could even write P here to mean that this is a box that has a P output, and we're trying to satisfy all the P inputs. So if we just generalize this a little bit, then we end up with what's called partial order planning. The way partial order planning works is you find an unsatisfied precondition and you satisfy it somehow. You find an action that achieves Q and you do it. So maybe there's a do Q action that gives Q, and we say, oh, well, okay, that's one way of achieving Q. We just do that do Q action. But notice that I instantiated this action after I had already done these two. Right? I already said, well, in order to achieve P, why don't I do P? And in order to do P, I'll need T. So how do I achieve T? Well, there's this do T action. That needs R, but R is already true in the initial state. So we're good here. Now I have a way of getting P. Now I'll work on Q. Where does do Q happen? Do I do Q after I do P? Or before P and after T? Or even maybe I just do it before I do T? I don't know. I'm leaving it kind of up in the air. This is not a fully sequenced plan. The order in which I'm instantiating actions is not exactly the reverse of how I'll do them or exactly the same as the order I'll do them. I'm just creating a partial order here. I'm saying do this, do T before do P, but at some point, would you please do Q? To actually execute this on a system, I'd have to linearize this partial order somehow, but that's trivial to do. So this is called partial order planning. We make a partial order. Everyone get it? Pretty straightforward. This was the dominant form of planning in the 80s and early 90s, and it's beautiful, absolutely beautiful, but no one's been able to get it to work fast. But it's just so beautiful that it's worth everybody knowing about it, and that they still have it in the textbook because it's really beautiful. It's also intellectually very interesting because what's actually going on here? What's the search space that's being searched? I have a plan, and then I select an open precondition, and I insert an action that achieves that precondition. Right? So in the node is a plan, and instead of waving my arms, why don't I draw a picture? Fresh sheet of paper time. Here I've got my little empty plan. That's in a node. So here's my goal with the things the goal needs, and the initial state with the thing the initial state makes available. And I pick a precondition, and I branch actually on all the ways of achieving it. So here I've got a plan where I insert action A to achieve that. And then here I've got a plan where maybe I'll insert action B to achieve that precondition. And there's some other open precondition that I haven't dealt with yet. Right? So every node is a plan. And to generate the successors in this search space, I elaborate the plan. I add actions to it. All right, so that's the search space of partial order planning. You pick a precondition, branch on all ways of achieving it. We haven't talked about threats yet. And then a goal node is a plan that has no open preconditions, where everything's been satisfied. You know how everything is going to get done. So this is to me, partial order planning is the most intuitive way of planning of all. You just find what needs doing and do it. Now, there could be many different actions that achieve a particular precondition that's open. And in fact, you might be able, let's go back to our more elaborate example here. If I need to achieve Q, maybe do T also, in addition to achieving T, also achieves Q. So one branch in the search space might not be inserting an action. It might be just selecting that action and making Q happen. Saying, okay, do T is going to be responsible for achieving Q. Let me talk a little bit about what this picture actually means. When we say that do T is responsible for achieving Q, this line here is called a causal link. So we're saying this do T action causes Q to be true. It achieves Q. And this line represents a commitment by the planner to not delete Q between the end of this action and the beginning of this one. During this interval, Q is sacrosanct. We can't quickly make it false and then make it true again by inserting other actions. This represents the commitment that this achievement of Q is the one that is necessary for this precondition. That's what inserting that causal link means. And if we were to interrupt Q here by something else, we would get that plan by inserting that other action here and then achieving this by going from over there. So both plans are possible. These causal links represent temporal constraints, saying, well, if this is achieving T for this action, then obviously it has to come before. If it's achieving Q for that action, it has to come before that one. So if we look at partial order planning more, do I have a little more formally? A partial order plan is a set of actions. It's a set of those causal links. And every causal link is basically also a temporal constraint. Now, let me talk for a second about threats. Let's say that I decide to achieve Q by do T. So that action isn't in the plan anymore, or didn't get inserted in the plan. Now let's say that there's something else I need to achieve, like maybe I need R over here. And I have some action here which, let's see. No, I'm hosed, actually. Oh, that's fine. I already have R. S. Let's say do P has another precondition S that needs to be achieved. So I have an S1 action that can achieve S. So what if S1 achieves S, but it also makes R, it also achieves not R? Okay, so I know that S1 has to happen before do P. But this not R effect, this deletion of R, is now threatening this causal link here. Because we needed R for this do T action. And this action is going to delete it. Right now, this action, all we've said about when it actually happens in the plan is that it comes before this. So it's actually threatening R here, which do T needs. So in addition to having to branch and make decisions about how we're going to achieve different preconditions, we now have a branch where we have to figure out how to deal with this threat. This is called threat resolution.
So do T does not produce not R?
Right. Not necessarily. It might, but as I've drawn it here, all it does is add Q and T.
So as long as S1 happens after do T.
Exactly.
Or do P.
So so it has to occur before do P, and one way of resolving the threat is to have it come after do T. Now, I guess this is the initial state. One other thing that people sometimes do is if this is an action that achieves R, you could move this before it. But in this case, this is the initial state, so we can't move it before. So the only possible way of resolving this threat is to add a little temporal constraint here, which is usually drawn with a dotted line. Maybe I'll do it in green just for fun. Add a little green line here. Doesn't really show up very well, does it? A little green line that says, by the way, this comes after that. So that's threat resolution. So this is all very intuitive, I feel. It's kind of a pain to implement. But the idea that, well, we should just plan by inserting actions that get what we want, and we're not generating all possible applicable actions. We're just instantiating the actions that achieve exactly what we want. And when the actions conflict with each other, then we can branch on ways of resolving them. It's pretty intuitive, but it's a very, very different search space, because now we're searching the space of plans. So the plan is no longer the path back to the root. The plan is the thing at the node. I guess I had that in this previous picture. Our search space right now has, and we're going to keep going here and instantiating more actions. Get more and more actions, and eventually we'll have a complete partial order plan that will have all the preconditions satisfied that we need, and maybe there'll be a little temporal link there. Anyway, this node will represent a plan, and that'll be our goal. So the way at which we arrived at the plan is actually of no consequence. The node itself has the plan. So we're searching the space of possible plans. Now, the space of all possible plans sounds like a big place. So maybe this would sound like a really bad search space. But one nice thing about it is that we haven't linearized anything that we don't have to. So if it doesn't matter what order we buy the eggs and milk, we're not going to generate two good-looking plans. We'll just generate the one plan where it says, oh, buy the eggs, buy the milk, do it after you came into the store and before you check out. But you can represent both plans, both linear plans, with a single partial order plan. So the set of states is actually smaller. Nathan?
I feel like you might be able to implement this, and the only thing you ever keep in memory is one state.
There are no states.
One node, I guess.
One node.
Yeah.
Yeah, there's this backtracking issue. I think I have an algorithm sketch somewhere. I think I have some pseudocode. Yeah. So you pick an unachieved precondition, then you find an action to establish it, and here's a branch. If you were using A star, for example, here's where you'd generate one kid for every possible way of establishing the precondition. Now you can choose whether you want to use depth first search or a best first search in this domain. What's the general rule of thumb that I think I was trying to push the first section of the class on? When do you use depth first? When do you use a best first kind of a search? Anyone remember the general rule of thumb? When you use what kind of a search? Do we have bounded depth here? No, we don't. So I would do a best first kind of a search if I were you. Yeah. I remember when I was a grad student, the planning assignment that I did well, actually, I never took an AI class, but the planning assignment that I graded as a grad student was a partial order planning assignment. And the algorithm was using A star, and the heuristic. You want to guess what the heuristic was in the state-of-the-art planner in 1994?
I don't know.
It was not H0. It was the number of unachieved number of open preconditions, which is basically analogous to the number of goal literals. So inadmissible, completely weak, non-powerful. Like you could barely solve problems with like 4 or 5 blocks in Block's world. It's pathetic. Nowadays we can solve Block's world for like hundreds of blocks. So we've come a long way in 25 years. That's not 25 years. Almost 20 years, 18 years. So anyway, so I would do an A star kind of a search because we don't know how many times we're going to have to achieve preconditions. So we don't have a good bound on the depth of the search. Other questions about partial order planning? Maybe I should finish going through the pseudocode. You have an empty plan, you pick an unachieved precondition, you branch on the ways to establish it, add a causal link between the action that you've chosen and the precondition you need for every threat. Either put the threat before the achiever or after the thing that needs the thing that you're threatening. If there's no place to put it, then this child is invalid. Here I wrote backtrack. What? Yeah?
Is that actual backtracking? Or
No.
or do you just try the next?
Yeah, this is... yeah, I should redo this slide. This is written assuming you know Prolog, basically, which I don't think they teach here in the programming languages class. I think 671 is technically a prereq for this class, which is technically our programming languages class, but we don't teach Prolog in our programming languages class, so it's probably not going to make any sense. Basically, just think of this as fail. Like, don't generate the child. Because here there's an implicit loop here where we're generating all the kids. So for every possible action, instantiate, copy the current plan, put in the causal link, look for threats, resolve the threats, then you have a valid child. So these are places where you would fail out of generating the child. Some people like to write algorithms in a non-deterministic way, but it's a little confusing if you haven't seen it before, and I don't think we've seen it before. So I should redo this slide to not do that. I apologize. There's one other tricky thing that's happening in this slide, which is this word right here. So there's in addition to being beautifully parsimonious in the search space, so like we're not making any commitment about what order things happen in until we absolutely have to. Traditionally, in partial order planning, the operators haven't even been ground out unless we absolutely have to. So, for example, if we need to be at the hardware store, so let's say I've got this buy drill. I think I need to be at hardware store in order to buy the drill. That's a precondition. And so to achieve at hardware store, I can instantiate the go action, which goes from somewhere to the hardware store. But I don't actually have to choose where my starting position is when I instantiate this action. I can leave that uncommitted. So this is a very different kind of planning. And the kind of planner you're writing, the first thing you do is ground out all your actions. So you have a zillion actions. Here, we leave the actions lifted and don't ground them out. And unfortunately, so that has good points and bad points. The bad thing is that if I have something else, like, how would I just buy a drill? If I have to buy nails, Well, no, let's see. What am I thinking of? Let's buy milk, actually. If I have to buy milk eventually, because that achieves have milk, which is something I needed for my goal, this achieves having the drill, and that achieves having the milk. In order to buy the milk, I think I need to be at the grocery store or supermarket. That's what I called it, at supermarket, in order to buy the milk. I know that going to the hardware store is going to delete being at wherever the place is that I started, but I don't know where that place is yet. So I don't know if that's a threat to buying milk at this point. Because I don't know if it's going to delete not at supermarket. I don't know if it's going to delete being at the supermarket. So partial order planning can't recognize that this is a threat for certain. What we can say, though, is that wherever this, if we're going to leave this hanging here, then this had better not be instantiated with supermarket. So that's called an inequality constraint. And so it's a possible threat, and you'd add an inequality constraint. So that's just a little complicated bit about partial order planning. But basically, it's trying to follow the principle of least commitment. So don't commit to temporal ordering if you don't have to. Don't commit to variable values if you don't have to. So that keeps the search space very small. In fact, someone has proven that partial order planning has the smallest search space size of any planning methodology that we've studied so far in this class. The reason no one uses it in practice anymore is because no one can figure out a good heuristic. Because you don't have any states. So like making a planning graph, how do you make a planning graph out of this? I don't even know what states we're going to go in. You might, if this plan is actually linearly ordered, but a lot of partial order plans are partially ordered, so you don't even know what states you're going to go through. So trying to figure out the distance to a full plan is hard to say.